In this video, I'll be talking about the motion of a charged particle in a uniform magnetic field. Or, or we will be finding out what is the radius of a particle when it enters into a magnetic field. How long does it take for a charged particle to complete one circular orbit? What is the time period? Or how fast it has to move to make a certain orbit? Everything will be talking into this video. So let us consider we have a region of the magnetic field. So here this cross represents the magnetic field here. When I say cross, that means the magnetic field is going into the paper. If I represent it by a dot, that means the magnetic field is coming out of the paper. So remember these two notations here. The cross means magnetic field is going into the paper or into the iPad here. And this dot here means the magnetic field is coming out of the paper. So you can remember this one by a nail here. So this is a nail. All right. So if you see this side of a nail, that means this nail is going into the wood, right? If you see this side, that means, or we can call this is a cross sign. If you see this side, that means it is going into the wood, that means into the paper here. Or if you see this point side here, that means it is coming out of the wood. So in this case, the magnetic field would be coming out of the paper. So these two notations keep in mind, and you can easily remember by using a nail or thinking about a nail. Okay. So here, as we have a region of the magnetic field, this region and the direction is given by cross, that means magnetic field is into the wood or into the paper. And let's assume this is the charged particle here, and the velocity direction is this one. So that's the velocity direction, or the charged particle has just entered this way. All right. As the charged particle is moving along this way and the magnetic field is into the wood, and there is a force acting onto it. The velocity and the magnetic field are mutually perpendicular, are both in perpendicular direction. Then there would be a force into it, and the magnetic force would be perpendicular to the both velocity and the magnetic field. How can we find out the direction? The direction we can find out again using a right hand rule. So this is a right hand rule. Right hand rule. So first thing you have to do, you have to have your index finger lie along the velocity direction and magnetic field in the direction, and middle finger in the direction of the magnetic field. Then your thumb points out the direction of the force, and all these fingers are mutually perpendicular. Okay, so you have to first set your right hand this way and align the index finger in the direction of the velocity. So in this case, this way. Sometimes you might have to twist yourself a little bit, and your magnetic field has to go into the paper here. Then your thumb will point out the direction of the force. If you do that, you'll find out the direction of the force is this way, and it has to be because the force has to be perpendicular to the velocity and to the magnetic field. So as the force is acting this way, the force will try to bend the direction of the charged particle. Okay, so it will bend into a circle here. Now let's see here, what is the direction of the magnetic field or magnetic force at this point? If the particle is at this point, the velocity is again in this direction, magnetic field is into the paper. At this point, if you use right hand rule, then the force would be again towards the center. So every time the force is towards the center, that means the force or the particle must be moving into a circular path. So this is the circular path here, and at each point the velocity and magnetic field and force are mutually perpendicular at each point. Okay, so you can easily find out using the right hand rule. So now we know that the magnetic force is given by this equation. Force is q v cross b vector. This is the force, and the magnitude is given by q vb sine theta. And in this case, theta is the angle between the magnetic field and the velocity vector, and both are mutually perpendicular, so theta is 90 degree. If angle is 90 degree, then sine 90 degree is 1. So we have this as the magnitude of the force. So we got this magnitude. But now remember, as this charged particle is moving into a circle, and I might have mentioned many times, nothing in the universe can move by itself into a circle. There must be some force that provides the necessary centripetal force for a charged particle or for any particle to move into a circle or into a circular path. Okay, so there must be something that is providing the centripetal force. So in this case, in this particular case, the magnetic force is providing the necessary centripetal force. Okay, so that means the magnetic force is providing the centripetal force. So these two forces has to be equal, or the magnetic force in fact is providing this centripetal force. What is the magnetic force here? The magnetic force we just calculated is Q, V and B. So this is the magnetic force. And we know the centripetal force is given by mv squared over r. Okay, so if I solve for the radius, then this is my equation here. The one velocity and this one will cancel out. So this is the radius of the charged particle. That means if the charged particle enters in a region of magnetic field, it will make a circular orbit, and the radius of the circular orbit is given by this equation. And now we can extract lot of information from this simple equation. What is that? The r is the radius, and it depends upon the mass, it depends upon the velocity. The mass times velocity is the momentum, which means greater the momentum of the charged particle is, it will move into a bigger circle, or the larger the velocity is, it will move into a bigger circle, or the larger the mass of the charged particle is, it will try to move into a bigger circle. And it is inversely proportional. R is inversely proportional to the charge. Also, R is inversely proportional to the magnetic field. That means if I put a charged particle in a stronger magnetic field, it will try to make into a smaller circle or make into a tighter orbit. The same thing happens with the charge. Greater the charge is, it will move into a tighter orbit. Okay, so Q and B makes it a smaller orbit or tighter orbit. The mass and the velocity will make into a larger orbit or looser orbit, or larger radius. Okay, so and it makes sense because the larger the momentum is, the larger the momentum of the charged particle is, it will be, or you need a stronger magnetic force to bend its path. Okay, and a stronger the magnetic field is, it will try to make a tighter orbit. So that's what this equation tells you. So we found out the radius. Now let's find out how long does it take to make this one complete orbit here. And here I'll introduce you a new term that is called the cyclotron frequency. This cyclotron frequency. What is the cyclotron frequency? The cyclotron frequency is in 1 second, how many complete orbit does the charged particle make is called the cyclotron frequency. Okay, the number of complete circular orbit the charged particle makes in 1 second is called the cyclotron frequency. In order to find out the cyclotron frequency, we'll find out the time period first. The time period. The time period means how long does it take for a charged particle to make one complete orbit, okay? Or the time to make one complete orbit is called the time period. And how do you find out? The time would be the distance. In this case, it is the circumference divided by the speed here. The circumference is 2 pi r of a circle, and that's the speed here. 2 pi r, and we know now. So radius, we already have found out the radius, which is mb over qb. So I'm plugging the radius here, okay? And this velocity and this velocity will cancel out. So we have this equation. That's the time period. And the cyclotron frequency is given by 1 over time period. So it is qb over 2 pi m. And now here, such an important point I would like to make. You see, the time period or the cyclotron frequency is independent of the velocity. It does not depend on the velocity at all. That means whether an electron is moving with 5 meters per second or 5,000 meters per second, 5 meters per second or 5,000 meters per second, whether the speed of the charged particle is 5 meters or 5,000 meters, it will take exactly the same time to complete one orbit. Okay, it will take exactly the same time. It might give you a little bit confusion. How come if it is moving with such a different velocity, how come it will take the higher velocity should complete in a smaller time, but it is taking exactly the same time? How come it is possible? The answer is, if the charged particle is moving with a larger speed, then it will move into a larger orbit. If the charged particle is moving with a smaller speed, it will move into a smaller orbit. As it is moving into a smaller orbit, it will take a smaller time. As this is moving with a larger speed, it will move into a larger orbit, and again the time period would be exactly the same in both cases. So what is the speed doing here? The speed is simply moving it into a larger orbit or into a smaller orbit, but the time period or the cyclotron frequency will be exactly the same. It is independent of the velocity. Okay, and here I mathematically shown that here too. Okay, so remember, if an electron is moving with a 5 meters per second or 5,000 meters per second, both electrons will complete the one orbit exactly in the same time. So this is it from this video here or this lecture. If you have any questions or confusion, write down your questions or comments in the comment section below. And do not forget to like, share and subscribe the channel. Thank you very much.